Okay, so you people can see now, isn't it?
Yes, sir.
Yes.
We
Yeah.
can see.
Okay, so how many people are there actually? Let me check first.
9.
Okay. Salman, Rishi, David, Fatima, Eduardo, Diego, Arusa. Okay. Okay. So, in the last lecture was kind of introduction as well, and still it will be going on a bit. And what you see here on this slide, that lecture number 2, okay? And so keep remember this, actually we are moving towards ultrafast lasers, okay? But I have to introduce some of the stuff because of some of the candidates here are not aware of with the lasers very well. And keep visiting the sites, especially the second one, this one, if you can, this one, okay. And so the things will be updated there regarding the course, etc. Okay, so let's move to the next slide. Okay, so what do you see here? I mentioned in the last lecture as well, a little bit, a few slides more about the history stuff. The dye laser. The dye laser was one of the important laser actually. And from dye laser, the concept of femtosecond laser was started. And it was, it can be, I mean, CW, it can be pulse, but the pulse one got more popular. So in 1966, actually, Peter Sorokin, he actually demonstrated the dye laser. And dye laser means you are using the dyes which we use for coloring the hairs as well, and the clothes and different kind of things. Rhodamine 6G or something like this. And excuse me. And this dye laser is usually pumped with another laser. So if you want to understand more, you can go through this video. Like it has, when it explained how actually dye laser, because this is not a scope of this these lectures here, so I'm not gonna go in detail of this dye laser configuration. And you can go to my channel that and you can see. Okay, so after that, I mean, the femtosecond concept actually was the dream of the scientists, because they wanted to generate the shortest pulses, and the dye laser actually, they gave this opportunity for the scientists to generate the shortest femtosecond laser pulses. Picosecond pulses were there, and nanoseconds were there, but femtosecond were only possible with using the dye laser. And after that, there are different configuration of dye lasers. I mean, how it can be used as a, to generate femtosecond laser, it's a bit complex. But when we move to the solid state like ultrafast laser, I will see that thing as well. Okay, so after that, okay, the most important laser, which we call the femtosecond laser, but the material which was important for to generate this kind of laser, solid state material, that was titanium sapphire. And titanium sapphire basically it's a key to generate femtosecond lasers. First time it was demonstrated at MIT, Lincoln's lab, and the person who first time introduced it, Peter F. Moulton. Okay, so you can see the picture of this guy here. Sorry. Okay, so you can see the picture of this guy here. And TISF laser, when first time it was introduced or demonstrated, it was for the CW, continuous wave lasers. Okay, but later on, it became as a promising tool to generate the shortest pulses, which was femtosecond pulses. And in this case, actually, the laser for pumping these titanium sapphire crystals, another laser is used, which we use, like anti-Yag laser, second harmonic of anti-Yag laser or something like this. And this was kind of a revolution at that time. And so later on, they figured it out that we can generate pulses by using this material, and that could be a very short pulses. So it's 1982, and after that, people started to work on it, and um, around 94, 95, 96, they started to generate the femtosecond pulses. Some more locking technique introduced. And Gerard Mourou, if you know the Nobel laureate, he actually worked on this TISF laser pulsed one to amplify and these kind of things. Okay, so move further. Petawatt laser. So basically, the petawatt laser, as I mentioned in my last lecture, this is a pulse laser. Obvious, when you say petawatt, it's a peak power. Excuse me, the weather is changing, so probably. Okay, so the petawatt laser, it's a peak power, as I mentioned in the last lecture. Today we will see more. It's very, huge peak power. And after the femtosecond laser, they were looking for this kind of dream to have a petawatt laser. And in 2010, if you see that the Lawrence Livermore National Lab, they introduced the petawatt laser. And that petawatt laser, probably they use at that time anti-Yag or mixed hybrid kind of system. And so this race of generating the petawatt laser is still going on. Okay. So terawatt, it's pretty common in these days. Okay. And when I was doing my PhD, so during that time, the terawatt, and I worked on terawatt laser system, the femtosecond pulses and terawatt laser systems. Okay, so the concept was started even at that time, but there was many technical issues to generate the petawatt lasers. And the first time the Livermore, and now currently, if you know that the ELINP, that extreme light infrastructure, nuclear physics, which is in Romania, actually, I was part of it. They are actually generating the 10 petawatt laser and using the TISF crystal only. Okay. So TISF crystals and petawatt, you can see here in the pictures, this one, this is a whole area. It's a clean room in the boxes you can see. These are the laser system amplifiers and oscillators and something like this. All this room actually, it's a big room. And if you open one of the box, you can see here, okay? Green, whenever you see the green, it means a pump. It's a pump for the TISAC crystal, okay? So it has multi-stages of amplification. Okay, so to reach to the 10 petawatt, they are moving towards the 20 petawatt as well. But nobody knows yet. And this is the present, current state of the laser development. We have petawatt laser, and this system actually, this system is not developed at the ELNP. System is it's from a French company. It's called Thales. So here mostly they are using this. Its installation was a huge kind of headache. Okay, so you can imagine petawatt. I mean, this is like you can have, if you generate the plasma with this kind of peak power, it's like a sun. Okay, so move further. There's a Britain actually, they have a program to generate 20 petawatt. Okay, so it's called the Vulcan system. It's not commissioned yet, probably. I don't know the detail, much of this system, but this is like 20 petawatt. They are planning to have 20 petawatt, and even I heard that in China they are planning to have 100 petawatt. Okay, to maintain this much peak power, to control this much peak power, it's not an easy job actually, and it's very dangerous as well. So these were the things which were missing in the last lecture when I was covering the history. So I thought to have it in this lecture a bit. Okay, so now if we move further, laser emission. So laser emission means, you know that laser, in the normal laser, it emits a single wavelength, ideally. Okay, so if you see here, okay, how many students are there now? Zanfar, Amina, Tahura. Okay. Zanfar, are you there? Zanfar, can you hear me? Anyway. So what we see here, that laser emission, and almost all the lasers, all the colors can be emitted with the laser. Okay, different kind of lasers. And the output you can see here, it depends on the lasing medium. Okay, what kind of medium is used, and it can be a solid, it can be a gas, it can be any other. Okay, and you can have different colors. Even some of the lasers, the tunable lasers, even you have a different color from the same laser, like I mentioned in the last lecture, the argonine laser. Okay, so we can have ultraviolet. Nitrogen laser can easily generate ultraviolet, and we can have violet as well. This is also with the argonine or some other excimer lasers, or this kind of laser you can have. Blue is very much possible with the diode lasers, and it's also possible to have second harmonic generation of the 800 nanometer. Second harmonic generation, the half of the wavelength. Probably you may not understand some of the students here, but it is. Okay, so the green one, very common. It can be generated with the semiconductor diodes, and it can be generated with the anti-Yag laser by using the doubling crystal. So doubling crystal is simply like laser is coming and you use a kind of non-linear material or medium. And after that, you can see the half of the wavelength of the input. Okay. So like this. And probably later on, I can explain you more. I mean, at this moment, it's not feasible or it's not appropriate somehow. Yellow is possible as well. Yellow, even with the helium neon laser, is possible. And orange, argon laser. And red is obvious. Red is helium neon laser and a ruby laser. And after that, you have this is infrared. And infrared is the most common one. Titanium sapphire, I mean, it generates infrared. And actually, if you see that ND-YAG, ND-glass laser, they are also actually generating a bit for infrared, which you cannot even see. In case of around 800, you can see red light or some kind of scattering in the red color. Okay, so these were we call it laser emission or laser line. If we move to the next slide now. So how we can categorize? How we can categorize the laser? You can see here the major way to categorize based on the material or the medium, the lasing medium. As I mentioned in the first lecture also. So laser can be generated in the solids, different solids. Laser can be generated in the gases. Laser can be generated in the liquids. Laser can be generated in the semiconductor diodes. Laser can be generated in the chemicals. Okay, means lasing medium. Okay, and in the last slide I mentioned that different colors are generated, different colors are emitted by using the different kind of lasing mediums. So major types of laser categorized on based on the lasing medium. Okay, so 4 types. Major, you can say. So first one is like solid state laser. Okay, and then you move to the liquid or dye laser or chemical laser. Okay, then you move the gas lasers. Some of the example I will show in the coming slides. And then you have some semiconductor or diode lasers. Solid state laser, if you see in the solid state laser, there are different materials, including the fiber optic. Fiber optics, the fiber optic laser is also considered as a solid state lasers. Okay. So all the people are listening or sleeping, by the way?
Active, sir.
Sir, we are listening.
Yes, sir.
Okay, thank you very much. Okay, so now we move to the next slide here. Actually, the difficult part of this course is not started yet. Okay. At that time, you may feel really sleepy, but at the moment, it's bit somehow simple things. So categorize the laser according to the lasing medium, solid state, liquid, dye, chemical, and you have gas laser and semiconductor and diode lasers. So if you see the liquid or the dye lasers, then there are many dyes. Okay, but the most popular one is this one. Okay, that is 6G. Rhodamine 6G. And this same dye actually used for coloring the clothes. Okay, and chemical laser, which is a category of liquids, is the most dangerous lasers to play with the chemicals. And high power, very high power lasers. So the examples are H2, okay, and HCl, the combination of these two. And can have a chemical laser. And the other one, which I mentioned, I'm just giving you some examples, okay? That is coil. Coil means chemical, oxygen, iodine, laser, okay? So very powerful laser. Weapon, great laser. First time when they started the concept to have weapons, they were thinking about it like for 60s to have a laser weapon actually. But it was not possible with only ruby or some other solid state materials, and also some other diodes, or with other like DICEF or something like this. For the weapon grade laser, you need high power. You don't care about the beam profile. Okay, beam profile mean how does it look like? Okay, it's very nice, it's very smooth. No, you don't need for the weapon this kind of laser. You need power. Okay, and this is a coil, and these are the CW, continuous wave lasers. And they tried this one, and they installed these facilities in different places, the coil, to use as a laser weapon. Even they installed this facility in aircrafts as well. Okay, so have airborne laser system or something like this. Okay, so after that, the solid state laser is the most popular, as I mentioned that. So it can be a ruby, it can be a ND YAG, ND glass. So what YAG stand for, that I will tell you later on, the later stages. And it's a yttrium something, complicated name. Okay, so ND glass and then TICEF. So the solid state lasers, these are the major category. Otherwise, there are some other as well. We have now in these days. And but these are the first one is ruby, then ND YAG, and ND glass is also very old, and TICEF as well. ND glass only used for the pulsed, to generate pulses of the laser, and the ruby also for the pulses. ND YAG can be continuous. Okay, so gas lasers, there are a couple of gases. The most famous one is helium neon, and we call it HENI, carbon dioxide, and nitrogen. So the carbon dioxide is also CW. In some cases it can be pulsed, but with certain techniques. And so nitrogen is a low power actually. It's pulse always. Nanosecond pulses, CW, the helium neon is CW. It can have a yellow, it can have a green, it can have a red, but mostly red. Okay, so in the category of semiconductor or diode laser, we have gallium arsenide. There are some other, but I'm not mentioning the names here. So these are like other semiconductors. So other semiconductors, same. I mean, they use a PN junction, P-type, N-type, or something like this. And it can be, you can see in the pointers or some other places as well. And semiconductor laser is promising even though it's not very much coherent. It's very promising because it's miniature size. It's a very small size, and it can use in many places, and it's not very harmful as well. Okay. Okay, let's move to the next slide now. So what do you see here? An overview of laser parameters, what we have seen in the previous some previous slides. So the carbon dioxide, its wavelength is 10.6 micrometer. Okay, and it's a CW, and it can generate from milliwatts to tenth of kilowatts. Okay, and it's very common in industries for engraving and for cutting as well. Okay, and it's a CW. Okay, the second one is ND-YAG. ND-YAG is 1.06 micrometers. So 1064 or something like this nanometers. And it's milliwatt to hundreds of watts. It can be used TW and can be pulsed. It depends. Because if you use as a pulses, you need a pulsed pumping source. Okay, pumping, you know, that is necessary for the stimulated emission. So whenever I use a pump, so you have to keep it in mind. Okay, without pumping, none of the laser will work. Pumping technique can be different. Okay. So here you can go up to hundreds of watts, and if you have a pulsed one, then you can have pulses in the range of a nanosecond. Okay, so peak power will not be very high. After that, move to the anti-glass. Anti-glass, it's a category of ND-YAG, and almost the same wavelength it emits, like here. And it can only generate pulses. Okay. And usually the anti-glass, I mean, it can generate the pulses, but to pump the anti-glass continuously is not possible. So you have to give some time, I mean, some seconds, some minutes each time. So it can only use in the pulse form, and it depends, but usually the pulse, I mean, it can go up to gigawatts or something like this. After that is a ruby laser. And ruby, the emission wavelength is 694.3 nanometers. Okay. And it's only pulse laser. Okay, you cannot have CW from the ruby laser. Okay, and it's not very high peak power usually. And it's not very common in these days. It was, I mean, a few decades back, but now it's not very common. After that, if you go and if you see here, that is a helium neon laser. And helium neon laser is 632.8 nanometer, which is a red color. And it's always CW. It's always CW. You can make it like pulse, but with some external arrangement. And it's not very high power in usual. It can be in some of the labs they have. In the normal labs, we use that in the range of microwatts to tenth of the milliwatt. It can go to the watts or something like this. And argon ion laser, which we have seen in the last lecture. This is 514.5, which is the central one. Okay, it can be tuned, it can go back, it can move forward, it can give you the blue color as well. It can also give you the red color. So basically, it's a CW. Okay, so it's not very high power. It's low power, milliwatts to tens of watts. And as I mentioned in the last lecture, it can be used in the laser shows. It was very popular before. Now other things are there as well. So 488 also exists with the argonine, as I mentioned, and it's also milliwatts to the watts. Then after that, you go to the krypton fluoride. Okay, and krypton fluoride actually is ultraviolet. The emission is in ultraviolet region, much more deeper actually. So 248 nanometer, which you cannot see definitely, and milliwatts to hundreds of watts. And after that, nitrogen, and yeah, so nitrogen laser is a gas type definitely. Krypton fluoride is also gas type, and this is 337.1 nanometer nitrogen, and it has only possibility to generate the laser pulses, nanosecond pulse duration. What is pulse duration? We'll see later. Okay, so these were kind of overview the laser parameters, which are these kind of lasers you can see in these days at different places or something like this. Okay, so if we move next, now, what do you see here? Continuous and pulse laser. I have mentioned many times. There are two kinds of laser that some of the laser emit continuously, and some of the laser they emit in the form of pulses. And some of the laser can have both the things. Okay. So pulse laser in these days are more popular because of high peak power. CW laser also used in some places, but it depends. In research related stuff, mostly the pulse laser are common. So possibility laser can operate either in a continuous mode or pulse mode. It depends. Or it depends on the lasing medium. And the pulse operation actually, it will give you high peak power. And this pulse system is used to achieve the higher pulse energy. Okay, because in a pulse, a huge amount of energy can be concentrated. Okay, so if you see in these diagrams here, this one here, it's a continuous wave CW laser. Okay, you can see here with the time it's not changing. Okay, so it has a zero frequency. Okay, like DC, and its output we measure usually in watts. Okay, can be kilowatt, it can be nanowatt or whatever it is, but watts. In the second figure here, you see the continuous waves, but chopped one. Chopped one means these waves were continuous, but we use kind of wheel on the way to the laser. Okay, and this wheel, it has holes. Okay, and it's rotated with a certain rotational frequency. Okay, so when you put this one on the way to the laser, then the laser is chopped. Okay, and if the laser is chopped, even though the actual laser is CW. So we cannot call it actually, it's really pulses. I mean, in some cases it can be if we have very good chopper, but we call it chopped output. In this case, because these are chopped, so we cannot measure the power continuously. Okay. So what we obtain or what we can measure in this case is average power. Okay. And in this case, in the first case, you can have you can measure the continuously power. Okay. So in this case, we need to have average power. Okay. But actually, if you take the power meter, usually they give the average power actually. Third one, if you see here, this is a pulse laser. Okay, these are the pulses of the laser. And these pulses of the laser, the energy or the power is concentrated at the peak. Okay. So that is why we call it the peak power. We can have an average power. We use the the power meter, and we can have, but that would not be an exact power of this pulse laser. Okay. So we need to know the peak power. So peak power is usually calculated from the average power or some other techniques. It cannot be measured. Okay. So CW here, chopped here, and pulsed here. Okay. So this one and this one, the important thing. You have output power, and here you also have average power actually, and you use a power meter. Okay. And here you will also you can have average power, but this average power is useless to measure here because you need to know the peak power. Okay. So you can see the peak goes high and the power is concentrated here. And that is usually much higher than the average power. Okay. Now let's move to the next slide here. Pulse laser. Okay. Our concern is pulse laser, ultrafast laser, pulse laser. Okay. So how we can have a pulse laser? Some of the material can have natural pulses to generate. Okay. But that is not usually very short pulses. Like ruby, or it's nanosecond or picosecond, whatever it is. We need something to generate the pulses. Some techniques, especially to generate some the pulses of the duration, what we need. Okay. So the pulses here, the conventional technique is Q switching, quality switching. Okay. What is Q switching? You'll see that. Other technique is a mode locking. With the help of Q switches or Q switching technique, we cannot generate femtosecond pulse. Okay. Number of reasons when we see the Q switching, then we can understand more maybe. So other technique, which is mode locking technique, sometimes it exists naturally actually. But sometimes we can have it by ourselves. So mode locking technique is used specially to generate the short pulses. Okay, like mentioned here, shorten the width of a pulse in a time, short pulse. Okay, So width mean like if this is a pulse, okay. So this width has to be short. Okay, so that would be a pulse duration. On the other hand, the Q-switch technique here, it mostly use to concentrate the energy to the pulse. But you cannot have a very small pulse. You want to generate a giant pulse, then you use the Q-switching technique. Okay. But if you really want to generate the femtosecond pulse, and after that you move to the attosecond pulses, it's not possible to use a Q-switching technique. So you need to use the mode locking technique. But here in the animation here, what you see here, this is mode locking. Okay, but you may not understand at the moment. There are many in the cavity. There is a cavity, and inside the cavity, there are a number of modes, a number of wavelengths are existing. So we have to lock that one. Okay. Probably it may not be able to understand for you people now, many of you, but maybe later on. On the other side, here this is an example of the Q switching somehow. You block the cavity for a certain time and then unblock it. It's a Q switching technique to generate a giant pulses. Okay. Okay. So this is how the Q switch can work. Okay. So we will see about the Q switching here, but the ultrafast laser, basically we use the mode locking technique. So this is very important sentence here, that pulse laser concentrate very high peak power densities, okay, due to the relative short duration of the pulse. Shorter the duration, highest the peak power. Longer the pulse, and less will be the peak power. So you shrink the pulse femtosecond and to more to attosecond, then you can have a much more higher. Attosecond cannot be generated directly, actually. It's a long story. But femtosecond is possible. So usually femtosecond pulses are used like 20 femtosecond, 25 femtosecond to generate a petawatt or this kind of lasers. Okay, pulses. Okay, so if we move next slide now, that will give idea about the measurement, power and energy. Okay, so we are focusing on the pulse laser now. Okay, so pulse laser, these are the laser pulses. Okay, you can assume. And this is the time. Okay, and here if we take a power meter, it will tell us the average power. Okay, and for how long time the pulse comes, pulse appears. So that is pulse duration. It's called pulse duration here, pulse width or pulse duration. And how much the gap between one pulse to another pulse, we call it rep rate, repetition rate. Okay, repetition rate. Keep remember. So average power is there. Use a power meter, you can measure the average power. Okay, but it will not tell you the peak powers or etc. etc. So these are the laser pulses, and the pulses appear here for a certain time. That is called the pulse width or pulse duration. Duration is for time, width, this width. Okay, both the words are okay. And what is the time difference between the one pulse to the other pulse? It's called the repetition rate. Okay. So to find out, okay, average pulse can be, but you need to know some basic formulas here. Energy actually usually measured in joules, okay? Energy per pulse, joules, okay? And the repetition rate, as I told you, after how long, or what is the difference between one pulse to another pulse, is a time actually, and time can be, from this time I can calculate the frequency, and that is F is equal to 1 over T. So this frequency is this one, okay? And this energy is this one. This is the basic formula if we want to calculate the average power. But we need to know the energy and rep rate, okay? Or what we can do, if we know this thing and if we know the average power with the power meter, we can find out the energy per pulse, okay? These are very important in the ultrafast laser, okay? How to make this kind of things, how to calculate, it's very simple. Repetition rate, always pulses. Laser is in the form of pulses. So repetition rate and pulse duration. And what is the energy? Energy, you cannot, some energy meters are existing. Okay, it's possible. But usually you need to calculate. Okay, so in the next slide is a continuation of power and energy. Let's assume that we have a pulse energy of 3 millijoule. Okay, 3 into 10 to minus 3 joules here. And rep rate is 10 hertz. 10 hertz is the frequency, okay, this one. Okay, so if we calculate the average power here, that is 3 millijoule multiplied 10 hertz is 30 milliwatt, okay? Or in some cases, we know the milliwatt, 30 milliwatt, and the repetition rate. Repetition rate usually we set. When we design the system, we set the repetition rate with certain calculations. You cannot set randomly, okay? So if we know this thing, if we know this thing, we can calculate the energy, which is important to know in laser systems. Move further, peak power. For the peak power, similar kind of diagram, if you see, the power is concentrating here, 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 okay? And energy per pulse is joule. And here we need to know the pulse width or the pulse duration, temporal length of the pulse, for how long time the pulse appears, how long time the pulse appears. So here, this is the formula to find out the peak power, okay? And energy, if we know energy, and we know the pulse, time, temporal length of the pulse, pulse duration, which is not easy to find out directly, that we have to make some kind of measurements, okay? That later you will see. But these are key formulas to find out the peak power. Energy we can find out from this formula, okay? We know the peak power, we know the rep rate, we can find the energy, and then we have to make some measurements to find out this T pulse, temporal width, and then we can find out the peak power. Here, one of the example, if we know the pulse energy 3 millijoule here and pulse duration, we make some measurements, and that pulse duration is, there is a mistake here. It is not hertz, okay? Pulse duration has to be in seconds, okay? That maybe I will correct in the next lecture. So then this is around 30 femtoseconds, okay? So this is by mistake, actually the pulse duration, what we make, what we measure it actually, it's a 30, I cannot write here properly. So 30 femtosecond. Okay, so 30 femtosecond, and this is the energy here, and we know the 30 femtosecond pulse. And then what is the peak power here? 10 gigawatt. You have a just milliwatt power here. Only because of the 30 femtosecond pulse duration, you have a gigawatt power, which you cannot obtain in a CW laser, and which you cannot obtain. The average power cannot be gigawatt in normal cases. Yeah. So this is the advantage of pulsed lasers. Okay. So I will finish here because the time is finishing. And if you have a quick questions, maybe you can ask. If any of you, or if you didn't understand anything, you can ask me in the next class or lecture, because this app, what I'm using, it will give me, it give me 10 minutes, 1 hour free. So if you have a very short question, or if you have anything to ask, or something like this, probably you can ask in general or whatever.
Or can we use high energy pulses? Like here, it is only 3 millijoule.
Yes. Yes, we can use. We can use.
Okay, sir.
Okay.
Thank you.
Yes, in the main